According to a new study, trapped electrons traveling in circular loops at extreme speeds inside graphene quantum dots are highly sensitive to external magnetic fields and could be used as novel magnetic field sensors with unique capabilities. Electrons in graphene behave as if they were massless, like photons, which are massless particles of light. Although graphene electrons do not move at the speed of light, they exhibit the same energy-momentum relationship as photons and can be described as ultra-relativistic. When these electrons are confined in a quantum dot, they travel at high velocity in circular loops around the edge of the dot. These current loops create magnetic moments that are very sensitive to external magnetic fields. The sensitivity of these current loops stems from the fact that graphene electrons are ultra-relativistic and travel at high velocity. The research paper is published in the journal Nature Nanotechnology. The research group at UC Santa Cruz used a scanning tunneling microscope (STM) to create the quantum dots in graphene and study their properties. The unique optical and electrical properties of quantum dots, which are often made of semiconductor nanocrystals, are due to electrons being confined within a nanoscale structure such that their behavior is governed by quantum mechanics. Because the resulting electronic structure is like that of atoms, quantum dots are often called artificial atoms. This research approach creates quantum dots in different forms of graphene using an electrostatic coil to confine graphene's speeding electrons. There are interesting potential applications for this as a new type of quantum sensor that can detect magnetic fields at the nanoscale with high spatial resolution. Graphene quantum dots can potentially host a giant persistent current, a perpetual electric current without the need for an external power source in a small magnetic field. Such current can potentially be used for quantum simulation and quantum computation. The study looked at quantum dots in both monolayer graphene and the twisted bilayer graphene. The graphene rests on an insulating layer of hexagonal boron nitride, and a voltage applied with the STM tip creates charges in the boron nitride that serve to electrostatically confine electrons in the graphene. Although the research lab uses STM to create and study graphene quantum dots, a simpler system using metal electrodes in a crossbar array could be used in a magnetic sensor device. Because graphene is highly flexible, the sensor could be integrated with flexible substrates to enable magnetic field sensing of curved objects.